Math 1325, we're moving on to chapter 6 today with section 6.1. We don't do every section in chapter 6, but this is one of them that we do cover. Section 6.1 is another point of view of the stuff we did in chapter 5. A big portion of chapter 5 was trying to find relative or local max and mins. And you can have many of those that aren't even necessarily unique to compared to each other, like one local max could be a little higher than another local max, which kind of defeats the purpose of the word maximum. But now you're going to get that other side of this. This is called absolute max and mins, or absolute extrema. If you want to say it in general terms, extrema. Max and min is more specific, where extrema just represents both of these at the same time. Absolute extrema. So there's a couple of cases to know. Sometimes what you're working with has a infinite domain, like this graph right here. This graph over here on the side, it's going up and to the left forever, and it's going down and to the right forever. So both the range and the domain are infinite. In cases like that, you're not guaranteed to have absolute max or mins. In fact, this has no max or no min because it literally goes up forever. So in essence, the maximum is infinity, but infinity doesn't count as an answer to what the maximum is, because infinity is just a concept that it goes on and on without ever stopping. You never actually reach infinity, even though some people think it represents the biggest possible number, but that's not actually correct. There is no actual value of infinity. It's just a concept that it keeps going forever. So if the graph goes up forever and if the graph goes down forever, then there's no max or min. And it could be one or the other too. Like in a parabola goes up forever, but it doesn't go down forever. So then it would have no absolute maximum, but it would have an absolute minimum, whatever this y value is. The values of absolute max or mins are y values, also not x values. So this one has no absolute maximum because it goes up forever, and it has no absolute minimum because it goes down forever. So just keep that in mind, that you're not guaranteed to get absolute maxes and mins whenever domains are infinite. But another side to this section 6.1 is having limited domains. And if a function or graph starts at a certain spot with a closed circle and then travels to another spot with a closed circle, this is what they call a closed interval. It has a limited domain. Maybe it goes from like -3 to +2 only. So the way that's written is, here's an infinite domain, -infinity to infinity. If you go from -3 exactly to +2 exactly, that's a closed interval. So intervals can be open, closed, or infinite. If I do -3 to +2 with parentheses, then it's an open interval. And that means you don't actually get to -3 or 2. You just get really close, like 1.99999. So that's an open interval. This is a closed interval. And an infinite interval can be infinite both ways or infinite one way or the other. Infinite. So like the basic x squared graph, the parent function for y equals x squared, that has an infinite domain, but the range is exactly 0 to infinity. So it's closed on one side, but it's infinite on the other. That does not count as a closed interval then. To be closed, you have to be closed on both sides. And if you're partially closed, partially open, or partially infinite, then it's not closed. Closed is a special case that we hope to get in this section, but then we can deal with the other ones that are not closed. But here is definitely a closed interval. There's two main rules in this section. And this is one of the two rules, that if you have a closed interval, it has to be closed. And then we always want continuous graphs at this point too. So if they're not continuous, that can be an exception case, but closed and continuous. If you're closed and continuous, then you're guaranteed to get an absolute max and an absolute min, both of them. And they're each unique as well. So unlike local maxes and mins, where they can be multiples of them and they can have different y values even, here you're going to be guaranteed to have one local max, one local min. Now there can be multiple x's that are tied for the max or min, but there's only one max y value and only one minimum y value in a closed continuous function. And then another key feature is it's not a long search to find them in this case, because they can only occur at endpoints of the closed interval or at critical numbers, which possibly could be local maxes or mins. So that's all we have to search for, is we're going to find all our critical numbers inside our closed interval, and there may be none or one or two or a whole bunch. And then we just have to also include the endpoints, and we just check what's the highest y value, what's the lowest y value of any of those spots, and those are the absolute max and min values. Remember that problem number 9 a few sections ago where it stumped me a little, because that was more like this section where the endpoints can be absolute maxes and mins, but they're not local maxes and mins normally in calculus. They just considered that there to be so because they said it was a practical problem about temperature. So that they were actually getting more into this section by doing that on that problem. Okay, so these 4 points are the only chance you have to have absolute max or mins, because they're endpoints and they're critical numbers where the derivative is 0 or undefined. You don't need to check anything else. And clearly this one's a little easier to do than what we're about to do, because the graph is provided for us. If we can see a graph, we can tell for sure where the highest and lowest points are. If we don't have a graph, then it might get harder then. But they want you to see this graphically first, so that when you do it algebraically and calculus-wise, then you'll understand why this is working as it does. So clearly out of these 4 points, the lowest one by far is this x1 value, because it's the only one that's even below the x-axis. So they can ask for either the location or the value or both of an absolute max or min. This one's just about the location because they're teaching you this for the first time. So x1 is the location of the absolute minimum, and it's called an absolute minimum because there's literally no other spot on this curve that's lower than that. A graph can have multiple relative minimum, and they can, if they're at different y values, then one of them clearly is not the overall minimum, and they might all be not the overall minimum, just in that area that they're the lowest points. But this absolute minimum, there's literally nothing lower than that anywhere on this graph. So whatever this y value would happen to be, they're not going to let me know it here. But if I knew what this y value was, either by looking at it or plugging it back into the function, then I would say the absolute minimum value is this negative y value, and it occurs at this negative x value, if they want both the location and value of it. But here we just have to say that x1 is an absolute minimum. And then x2 is not quite as high as x4 is. So that can't be an absolute maximum. There's a point that's higher than it in the interval that I'm working with. This would be a relative maximum because it increases first and decreases after it. This x2 is a relative maximum, but it's not an absolute maximum. x4 is higher. So x2 is neither. It's nothing special if you care about absolute ones. It is special if you care about relative max and mins, but it's not special if you care about absolute max or mins. Same thing with x3. There are spots that are higher and lower than x3, so that's nothing special. And finally, x4 is my one and only absolute maximum. And there can be a tie for the absolute min and max in terms of x locations, but there's not multiple different y values for absolute max and mins. There can only be one of those each. And if you have a closed continuous graph, then you're guaranteed to get the one absolute maximum value and the one absolute minimum value. So that's what's about to happen here on number 3. I have a polynomial function. We know from algebra that polynomials are continuous and smooth curves everywhere. They don't have any domain issues. And we do have a closed interval given to us. So we're guaranteed to have one absolute maximum value and one absolute minimum value. And there could be multiple x's that create those, or maybe there's just one x that creates each one. But we're guaranteed to get one of each for sure now because we have a closed interval on a continuous graph. So first thing I'm going to do in number 3 is we got to find all the critical numbers just like we did back in chapter 5. That's always the key to a lot of this. Get your critical numbers. X to the third, 8x squared, 16x, and 8. So first I'm going to find the derivative of this function. 3x squared plus 16x plus 16. This is a polynomial itself. It's never undefined, but it could be 0 twice. So I'm going to set it equal to 0 and look for the two zeros. Now this could be 3x times 1x. That's all you could do with that part, if it even factors. And this is plus, so you're going to get two of these, two pluses for sure. Now it could either be 1 and 16, or 2 and 8, or 4 and 4. Usually I just try the most common way first, 4 and 4, and then if that doesn't work, I can try 8 and 2, or 16 and 1. But there's 4 and there's 12. 4 plus 12 is 16. So that is how it factors. They usually give you ones that factor. I mean, if you were really in a calculus 1 class instead of a business calculus class, then you might have to employ the quadratic formula sometimes on these where it doesn't factor evenly. And we might get one of those in our business problems where they put real messy decimals a lot of the time. But any of the ones where they're just teaching you the strategy at first, you're going to get ones that probably factor. So I'm going to get two x values that make this thing equal 0. One of them is obviously -4. And then this one you have to subtract 4 and divide by 3. So here are my only two critical values of the entire domain. But I might not even work with both of them, because I'm limited to this -6 to 0 closed interval. Any critical number not in this range, we don't care about it. But both of those are in this range. But if either one or both were not, we would throw them out. So we have two critical numbers in our range, and we always have the two endpoints. So you're basically just going to make a chart here. Put the two endpoints and any critical numbers in between, whether there's none or 1 or 2 or a whole bunch. So -4 and -4/3. And all you have to do is plug them back into the original function, not the derivative, but the original function. Whatever one of these 4 answers is highest or tied for the highest is the one and only value of the maximum, absolute maximum. And if there's a tie for the highest, then I'm going to have multiple x's that are doing it, but it's still only one y value that it's happening at. And then I'll do the same thing for the minimum. So you basically just have to calculate all 4 of these and see which answers are highest and lowest. So first I'm going to plug in -6 and do -6 cubed plus 8 times -6 squared plus 16 times negative 6 plus 8. Turn on the light so I can see a little better. Okay, so I typed in negative 6 where all the x's are. And equals, I just got negative 16 for an answer. When I plugged in negative 6, I got negative 16 for a y value. Now change the negative 6's to negative 4's. Now the y value is positive 8. For 0, it's going to be easy. The answer to 0 is this 8 right here. So we already have a tie so far, but maybe this one will beat both of those. Now put negative 4/3 in for all the x's, and I've got negative 4's already, so I can just insert a divided by 3 on each one. Insert a divided by 3. Insert a divided by 3. And if it's a messy decimal, it won't matter if it's not one of the answers, but if it is one of the answers, math, enter, enter. It's negative 40 over 27. But as a decimal, it was negative 1.48. It's not one of the answers. So we have one unique lowest value here. Negative 16 is the absolute minimum. So the way you answer this is you say there's an absolute minimum of negative 16 at x equals negative 6, which happened to be one of the two endpoints. At this point of the process, you don't care whether you're getting it from a critical number or an endpoint, but those are the only places they can happen at. And then there's a tie for the absolute maximum value of 8, but we only list the value once, and it's occurring at both negative 4 and 0. Absolute maximum of positive 8 at both negative 4 and 0. That's how they generally like these answered. There's an absolute maximum value of 8 at both 0 and negative 4. So you just separate the answers with commas. They use a comma to separate answers. Round to 2 decimal places. I guess if you do get that decimal one, they would have wanted the decimal here instead of the fraction, but sometimes they prefer the fraction. And then there's an absolute minimum of negative 16 at negative 6. But there can only be one maximum value and one minimum value for absolute ones, even if it happens at multiple x values. Okay, similar problem in number 4. We got a 2x to the 4th minus 64x squared minus 3, and our closed interval is negative 5 to 5. X to the 4th. Oh, sorry, 2x to the 4th minus 64x squared and minus 3 from negative 5 to 5. Closed interval, we have a polynomial that's continuous everywhere, so we're definitely going to get one absolute maximum and one absolute minimum in this closed interval. The derivative is 8x to the 3rd minus 128x. That's never undefined, but it could be 0 3 times. I'm going to factor out an 8x and leave x squared here. Hopefully this divides by 8. 128 divided by 8 is exactly 16. So that factors one more time with difference of squares. X squared minus 16 is x plus 4 and x minus 4. So we have 3 potential critical numbers. If we were working with the whole domain, there would be 3 critical numbers. We have a limited closed domain, so we may not be using all 3 of these. but actually we are because the domain is -5 to 5. So if the domain had been -3 to 3, then I would only be using 0. So you always have the two endpoints on a closed interval. And then you can get anywhere from 0 to as many as you can think of critical numbers in between. But usually it's like a handful or less, for us anyway. So -4, 0, and 4. I've got 5 x values to try to find f of x of. And 0 is the easiest one because the answer is just going to be -3. And the exponents are even, so as soon as I plug in 4 and 5, the other answers are going to have the same values. So 2 parenthesis, I'll plug in 5 first, 5 parenthesis raised to the 4th power, minus 64 parenthesis 5 parenthesis squared minus 3. When I plug 5 in, I'm getting an answer of -353. Well, that means the other one is the same thing because plugging -5 in, the even exponents are going to create the same answers. Then I can press second enter and just change the 5s to 4s. And this will be the answer for both 4 and -4. This is -515. -515. So this time the endpoints are not maxes or mins. And it doesn't really matter if you're getting answers from endpoints or critical numbers, but the first time the maximum, we had a tie for the maximum at a critical number and at an endpoint. The minimum was at an endpoint, but now neither of the endpoints are anything special. The absolute maximum is -3. Absolute maximum of -3 at 0, which is one of the critical numbers. And then there's a tie for the absolute minimum. There's an absolute minimum value of -515. We only say that once though, but it occurs at both -4 and +4. And what's really happening here is if you know how x to the 4th graphs go, x to the 4th are big W shapes. And they're not always totally symmetrical like this one is, but sometimes they're symmetrical like this. Other times they can be like this, where it's lower on one side than the other. But if it's symmetrical, and this is from -infinity to infinity, but maybe -5 is here and maybe +5 is there. So you're starting at -5 with a closed interval, and you reach the absolute minimum right there at -4. It started off at -300 something and dropped to -500 something. And then it's 0, so this is actually, what was the y value at 0? 0, -3. So the x-axis must be like so. And that way, this coordinate right here is 0, -3. And that's the highest you ever reach from -5 to +5. If you keep going past that, there is no maximum because it goes up forever. But if I have a closed interval, then those infinite things don't matter anymore. And then because of the symmetry, this is also a absolute minimum spot, although the value is still the same thing. The y value is the same at both of these. If we had one like this would be the only absolute minimum. And this could be the absolute maximum again if we went like from here to there, for example. But back in chapter 5, we would call this a local minimum and this a local minimum, even though their y values are different. And this would be a local maximum in chapter 5. So that's kind of what's going on here. But if you have a little knowledge of how the graph goes, that can help make you understand it a little better. Okay, so go back to your chart to get the answers. They always want the maximum first, apparently. The absolute maximum is -3 at 0 only. There can only be one maximum value, but the x's, it can be a tie at a bunch of x spots where it's occurring. Here we only had one x value that created this absolute maximum. The absolute minimum was -515, and it occurred at both -4 and +4. Okay, what if we get a rational function? We still have a closed domain of 0 to 8. F of x is 4 minus x over 8 plus x. And we're going from 0 to 8. Yes, 0 to 8. So first I got to find the derivative. And this is a quotient, two functions of x divided by each other. So I would do second times the derivative of the first. The derivative of the first is just -1, since that's linear, minus the first. The derivative of the second is just 1 times the derivative of the second, and then over the second squared. If I clean up the numerator, this would be -8 and -x, or if I want to put the x first, maybe -x minus 8. And this 1's not going to matter, so this is -4 and positive x. The x's cancel. You could even rewrite this one x plus 8 if you like that better, since addition is commutative. So the derivative function is -12 over x plus 8 squared. The derivative function never equals 0 because the top is always going to be -12. A fraction only equals 0 if the top is 0 and the bottom isn't. So the top can never be 0 because there's no x to plug in for it. And then anything squared is positive. So the derivative is always negative no matter what. No matter what x you plug in, the derivative is always negative. That means this function is always decreasing over its entire domain using chapter 5 knowledge. Then the denominator could equal 0 at -8. If x was -8, then we would get 0 in the denominator. That would make the derivative undefined. So -8 could be a critical number, except it also makes the original function undefined, so then it's not a critical number. So we have no critical numbers. No critical numbers. But even if -8 was a critical number, we wouldn't use it anyway because -8's not in this domain. So that was going to always be out no matter what. So we only have two values to check, the two endpoints literally. So for sure, one of them is going to be a local an absolute maximum, and the other one's going to be an absolute minimum. We have no other option because on a closed interval of a continuous function, you have to get one absolute maximum and one absolute minimum. It's guaranteed to happen on a closed continuous interval. So because those are the only two numbers I have to check, then for sure one of them is the max and one of them is the minimum. Plug 0 into these two x's right here, and you're literally going to get 4 divided by 8, which is 1/2. Or if they want decimals, 0.5. Plug 8 in, you're going to get 4 minus 8, -4. 8 plus 8, 16. That's -1/4 or -0.25. -0.25. So this is the absolute minimum. There's an absolute minimum of -1/4 at x equals 8. And there's an absolute maximum of 1/2 at 0. That's what the calculus side of this is telling me. Absolute maximum, whether they want decimals, yeah, decimals. So I don't know if they would take 1/2, but the absolute maximum is 1/2 or 0.5. Since they said decimals, I'll put the 0.5 in there. And that occurred at 0. The endpoint of the beginning of the interval. And then -0.25 was the lowest it ever got, and that happened at the other endpoint of the interval, 8. And if you have knowledge of the graph of this thing from college algebra, This is a rational function. It has one vertical asymptote at -8, which isn't even in our range. It's got a horizontal asymptote of -1 because you'd have to divide the leading coefficients. There's a -8 vertical asymptote, a -1 horizontal asymptote. When x is 0, y is a half, so that would be right there. So this thing would probably go like this. And we could plug more x values in if we wanted a detailed graph, but remember how the derivative was always negative? So this graph is always decreasing. It's just going down, 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 all the way. If we allowed the domain to be all real numbers, which is normally the case for this graph, then there would be no absolute maximum or absolute minimum because it goes up forever and down forever. But we have a limited domain. We're starting exactly when x is 0, and we're ending when x is 8. That's our closed interval to work with. And notice the highest it ever gets is when you start that interval, and it keeps going down, 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 down. The lowest it ever gets is when you stop counting at 8. So when x is 8, you've reached -0.25. When x was 0, you started at 0.5, literally. So this makes sense on the graph, that if you know how this graph works. Okay, what if I get fractional exponents? I still have a closed domain here on number 6. -2 to 1, so we're guaranteed to get an absolute max and an absolute min. (17x to the 6/11) plus 6x to the 17/11. So and I got to put my domain down. We have a closed domain interval of -2 to 1. So the derivative would be 17 times 6/11 x to the 6/11 minus 1. That's literally doing the power rule right there. And then 6 times 17/11 x to the 17/11 minus 1. Nothing simplifies here, so 17 times 6 is 102 over 11. And I would change this 1 to be 11 over 11. Anything divided by itself is 1, so then you would have 6 over 11 minus 11 over 11. That's -5 over 11. And then this is 16 times 17. 6 times 17, that's also 102. That's weird. Okay. 102 over 11 for that one too. And x to the negative, again, make this 11 over 11. Actually, it's not even negative. It's 17 over 11 minus 11 over 11, which is 6 over 11. So what we can do here is a greatest common factor. They both have a 102 over 11. And then when you're doing variable greatest common factors, it's always the one with a smaller exponent. So the greatest common factor is the smallest exponent for variables. And clearly a negative is smaller than a positive. So this entire term is the greatest common factor. And anything divided by itself is 1. This divided by that is 1. But when you do x to the 6/11 divided by x to the -5/11, there's a rule of exponents for that. X to the 7th divided by x to the 5th, that's when you subtract the exponents and get x to the 2nd. Literally 7 minus 5. So if you do x to the 6/11 divided by x to the -5/11, you're going to get x to the 6/11 minus, literally minus a negative 5/11. It can be minus 5/11 or minus negative 5/11. It could be either one. This is minus a negative, that's plus. 6/11 plus 5/11 is 11/11, which is 1. In other words, just x. That helps to just have an x here instead of having a messy radical. So we can set this equal to 0. One of our critical numbers is going to be x equals -1 from this part. This here equals 0 when x is -1, and -1 is in our interval of question. This other part, if you set this equal to 0, 102 over 11x to the positive 5/11. If you move it to the bottom, it would be positive 5/11. Well, that's only going to equal, if you plug 0 in for x, that's the only thing that would cause anything to happen here. The top is never going to be 0 because it's just a 102. The bottom would equal 0 if x is 0, and that makes the whole thing undefined. So that could, in theory, be a critical number, and it is in the interval between these two. But in the original, does it make the original? No, it doesn't. See, so the original would not be undefined by plugging 0 in because both of these exponents are positive. So 0 is another critical number. So I have one critical number coming from an undefined derivative, and I have another one from a 0 derivative. So it doesn't matter where they come from, but I have two critical numbers and they are both in the interval. So then I'm going to need to make an f of x chart, and you always have your two endpoints no matter what if it's closed. And then I've got two critical numbers to add to the list. So all four of these need to be plugged into the original. And whatever the highest and lowest answers are here, even if there's a tie, those are the absolute max and mins. And 0 is nice because 0 to any power is 0. This is just going to be 0 plus 0 if I plug 0 in. So the y value is 0, 4, 0. If you plug 1 in, that's nice too because 1 to any power is 1. So you'll get 17 times 1 and 6 times 1. That's 17 plus 6, that's 23. For -1, the 11th root, luckily these are 11th roots because then you can plug negatives in. Normally an odd root of -1 is -1. And then when you raise it to the 6th power, it would turn into +1. So that would make this part 17. But when you raise it to the 17th power, that'll be -1. Times 6 is -6. So 17 minus 6 is 11 when I plug in -1. And -2, there's no nice answer to that at all. So 17 times -2 raised to the 6 over 11th power plus 6 times -2 raised to the 17 over 11. And I could have done this for the -1 also, but, or even the 0, 1 if you didn't know the answer. And it's just a messy decimal, and that's why they are taking decimals for answers here. 7.297. But that won't matter because it's not the highest or lowest answer. The highest answer anywhere in this list is 23, so that's the absolute maximum. There's an absolute maximum of 23, and it happens at a unique x of +1. There's an absolute minimum of 0 at x equals 0. And one of those was an endpoint, another one was a critical number, and it was even the critical number that caused the derivative to be undefined instead of making the derivative 0. And again, that detail doesn't matter, but the good thing is that's the only times you can get these answers. They have to occur at endpoints only or any critical numbers that are inside your interval. If you have a closed domain on a continuous function is the only way that rule applies, but every problem they're giving us so far has had that. So 23 is the absolute maximum value, and it occurred only at the interval of 1, or the x value of 1, I'm sorry. 23 occurred at 1. 0 occurred at 0. Okay, so next level up is what happens if you don't have a closed interval. So one of two things could happen. If you happen to know what the graph looks like, that could be your solution. If you could graph this and just take a look, where does it reach its highest? Where does it reach its lowest over this entire domain? Because this is an infinite domain. Or there is another rule, actually, that I'll tell you about as soon as we check for critical numbers here. So this rule works on any interval, but it's more important when you don't have a closed interval. When you have a closed interval, you should just do the endpoints and all the critical numbers in between. That's the best rule for that situation. This next rule works anytime, but it has a very special condition on it that has to occur that usually does not occur actually. So in theory, you could possibly use this rule on those first 6 problems, but it's a very special case. And thinking back to what happened on those problems, I don't think it ever came up actually. But in theory, this might work on what we did on the first 6 problems. But what we did on the first 6 problems definitely will not work here. The big condition for that is you have to have a closed interval. This is not a closed interval. This is an infinite interval. We're going to go from 0 all the way to infinity. And 0 is not even closed. This is literally 0 to infinity opened versus an infinite side of your domain. So you have to have closed on both sides to use that first rule. Okay, so what would be the derivative here? First, I would rewrite this. Before you do the derivative, I don't want to do a quotient rule here unless I have to. This isn't a quotient rule if you rewrite it as 8x to the negative 2. Because you don't have x in the top and the bottom is y. It would work if you did the quotient rule. It's just a whole bunch of work for nothing. So I'm going to rewrite the original function in an easier way to do the power rule. And now do the derivative of that. The derivative of 2x is just 2. The derivative of 2 is nothing. And this derivative is the power rule, negative 16 x to the negative 2 minus 1, which is negative 3. And this plus a negative could just be minus. So probably the best way to write this now would be 2 minus 16 over x to the third. That's the derivative. So I want to know, when is this thing 0 or undefined? So it's only undefined if x equals 0. That would make this denominator 0. As soon as the denominator is 0, the whole thing is undefined. 0 is the only number that makes this thing undefined, but it also makes the original function undefined. Plus, it's not even in my interval anyway. So 0's out for a couple of reasons. So the only thing left then is what makes this thing equal 0, if anything. And I'm not going to use endpoints here. You can't use endpoints unless you have a closed interval on both sides. So once there's not a closed interval, then endpoints go right out the window. You're definitely not going to use endpoints either. So I could add this fraction to the other side and turn it into a positive. I could put this 2 over 1 and just cross multiply like back in geometry. 2x to the third would equal 16 times 1. You could divide both sides by 2. X to the third equals 8. The cube root of each side, cube root of 8 is 2. So I have one and only one critical number. 2 is the only one, and it is in this open interval too, this infinite interval. So here's the other rule. The first rule is, maybe I'll make a list here. Closed continuous interval. Closed continuous interval. This is called the extreme value theorem. Extreme value theorem. Then you're guaranteed to get an absolute max and an absolute min. There'll definitely be one of each and only one of each, although the x's can tie for the times that is occurring, but the values only happen once each. And then you just check endpoints. Both of the endpoints are always in play. And sometimes both answers are the endpoints only. We saw one of those, but sometimes neither of the endpoints are an answer. Endpoints and critical numbers, and only critical numbers inside the interval too. Critical numbers inside the interval. That's what you're looking for. And you're guaranteed among whatever long list you have there, you're going to have 2 or more of those possible x values no matter what. There's going to be 2 or more of those, depending on how many critical numbers are in between. Out of all those possibilities, there's your absolute maxes and mins. If you have any interval at all, whether it's open, closed, or infinite, doesn't matter, but it's more useful when it's not closed, because if it was closed, I would use this. Any interval at all, open, closed, or infinite, this is called the critical point theorem. Critical point theorem. Here's the whole key to this one. If only one critical number in this interval, if your interval only has one critical number, even if there's other critical numbers that exist outside the range, doesn't matter. But if there's only one critical number in your interval, and if you check whether it's a local max or min, if only one critical number and it turns out to be a local or a relative max or min, then by default, it will automatically also be an absolute max or min. Then it becomes, and you can only get one or the other, not both. Oops, absolute, I was trying to write max and min, but I started to mess up. So absolute max or min. It's only one or the other, because you only have one to work with. Something can't be a local max and a local min at the same time. So, and it may not be a local max or min. So if you get this, like we just did a second ago, we got only one critical value inside our open interval. So I'm not guaranteed to get anything right now. This could be nothing. So I need to check whether 2 is a local max or min the way we did back in chapter 5. If it turns out to be a local max or min, then automatically, since it's the only critical number in my interval, then by default it has to also be an absolute max or min. So this is not a surefire way to get an answer, but it's really our only last resort, really. And then we have 2 choices. We can either work with the first derivative and do the first derivative test, or if it's easy to calculate the second derivative test is a little less work. But with this, probably that's going to be more work, so I'm just going to do the first derivative test. So first derivative test, you put the one critical number down, 2, and I would try, now you can't plug 0 in because it's not part of the interval, so I would try 1 and 3. If I plug 1 and 3 into the first derivative, if one side is increasing and the other side is decreasing and vice versa, then I have a local max or min. So if I plug 1 into the derivative, that's easy here. 1 cubed is 1. 16 divided by 1 is 16. 2 minus 16 is negative 14. The derivative is negative for my test point of 1. That means the function, the original function, is decreasing at first. It's decreasing till I get to this critical number. Maybe it's going to decrease after the critical number. That can happen. But if it increases after the critical number, then I'm going to have a local minimum there. And then because this is the only critical number in the whole interval, then it's also an absolute minimum as well. So plug 3 in. 3 cubed is 27. 16 divided by 27 is somewhere between 0 and 1. And 2 minus that is definitely positive. We don't care what the answer is, just is it positive or negative? It's definitely positive. So you're decreasing, then you have that one moment in time that you're flat because I have a 0. This came from a 0, not from an undefined spot. So it's flat right there for that second, and then it increases after that. So by the first derivative test of chapter 5, I have shown that 2 is a local minimum. 2 is a local minimum by the first derivative test. And then by the critical point theorem of chapter 6, it's also an absolute minimum, since it was the only critical number in the interval. And none of the other problems that we did so far, this one had no critical numbers. This one had 3 critical numbers. And you always have the endpoints here when they're closed, but this one had 2 critical numbers. So if you happen to notice while you're doing this method, if you happen to notice there's only 1 critical number, you could use the other rule then at that point if you wanted to, if you think that's less work. But that other rule, the second rule, doesn't work very often on closed intervals because often there's 0 or more than 1 critical number. But if you are doing the extreme value theorem and you happen to notice there's only 1 critical number, you could then resort to the second rule. The only problem is that's only going to give you one of the 2 answers. That's the other thing, is you're only going to get one of these 2 answers at the most if you're using the second theorem. And in these problems, when there's a closed interval, you're guaranteed to get both answers. So that would only help you get one of the 2 answers anyway, and then you'd still have to do this rule anyway. So that's why if it's a closed interval, you're just going to use this theorem every time. If it's an open interval or an infinite interval, then your only hope is this, and it's still not even guaranteed that you're going to get anything. You could do it on a closed interval, and if you get only 1 critical number inside the interval and it turns out to be a local max or min, it would also be the absolute max or min, but then you wouldn't have the other answer. The other answer is the problem. So keep in mind that this critical point theorem, it does work for any interval, but it's not really useful for closed intervals. So 2 is the absolute, whoops, I don't need to do this. 2 is the absolute minimum. Well, actually not 2. X equals 2 is the location of it. So I need to plug 2 into the original function to figure out what the value of it is. 2 squared is 4. 8 divided by 4 is 2. 2 plus 2 is 4. And 2 times 2 is 4. So 4 plus 4. There would be an absolute minimum of 8 at x equals 2. And it could never be lower than that anywhere else, no matter what, from 0 to infinity. Now, there may or may not be an absolute maximum, but I can't tell from this. So I guess you just say no. I don't know if it guarantees there's no maximum, but apparently, okay. So no maximum. But you're never going to get both of these answers if you're using the critical point theorem. It's only going to help you get one answer because the whole key is there can only be 1 critical number in the interval. And therefore, you can only get one or the other, not both. So let's try this for number 8. And then our 9 and 10 are business application problems. So number 8, I've got 2x to the 4th, 2x to the 4th, minus 8x to the 3rd, minus 40x squared minus 1. And my interval is apparently infinite because they don't mention anything. And these are polynomials, so normally their domain is infinite. So you got an infinite domain on any polynomial. So I can't use the extreme value theorem because I don't have a closed interval. Remember, I was actually drawing one of these earlier. Where was my W shape? See, normally these things go up forever, or maybe down forever if they're upside down, but the reason it worked here was we closed the interval. We just arbitrarily cut this thing off at 2 spots. That forced an absolute max and an absolute min. But if you use the entire domain, you may not get a max or a min, actually. You won't get one or the other, actually. This one's going to have no maximum just because I know from the graph that this is a W shape opening upward. So there's only going to be possibly an absolute minimum here. So let's find critical numbers. Okay, so actually I'm thinking of something right now, but let's find critical numbers. So 2x to the 4th, that would be 8x cubed, minus 24x squared, minus 80x. That's the derivative. It's never undefined because it's a polynomial. If I set it to 0, maybe there's 3 zeros to this thing. So 8x appears to be the GCF. That would leave x squared minus 3x minus 10. Okay, so this should factor again. There's a negative in the back, so we're going to get 1 positive, 1 negative. Multiply to 10, subtract the negative 3. That would mean the negative is the bigger of the two numbers. So positive 2 and negative 5. Positive 2 and negative 5 are the factors. So we have 3 zeros actually. 0, negative 2, and positive 5. So actually neither of the two theorems would work here. I don't have a closed interval, so I can't use the extreme value theorem. And I have an open interval, but there's more than one critical value in the interval. So the critical point theorem doesn't work. So I guess the only thing you could do here is just use your college algebra knowledge. And we know that these two x to the fourth graphs, they take W shapes and they may not be symmetrically like this. So these three critical numbers, these are local maxes and mins. And this thing goes up forever to infinity, so it definitely has no absolute maximum no matter what. One of these two local minimums has to be the absolute minimum just by my college algebra knowledge of how these polynomial graphs are drawn. So I don't even have to check the 0. This 0 is going to be that absolute, it's going to be that local maximum. 0 is going to be the local maximum. Negative 2 and positive 5 are two local minimums just based on my knowledge of how these graphs go. And it could be a tie like it was before. Remember before we had a lot of symmetry going on. And both of these were the same in this other problem. But they may not be the same here because of the way they're different values, 2 and 5. So all we got to do is plug these two into the original function and see what the y values are. 2 times 5 to the 4th power minus 8 times 5 cubed minus 40 times 5 squared minus 1. The y value is negative 751 when you're at x equals 5. And then if I repeat this for negative 2, negative 65. So again, if I didn't know what this graph looked like, then I could be in trouble here because then neither of the two theorems of this section works. But this is kind of your last resort then. You might need to use college algebra knowledge and graphing knowledge in order to figure this out, like the first two problems. The first two problems where they gave us graphs. So apparently this graph, like we would do in college algebra, it comes down and it goes back up at 0, and then it comes way down at 5, and it's some kind of graph like this. When x is negative 2, the y was negative 65. And when x is 0, we could easily tell what the y is, but that's not going to matter here. The y would be negative 1 there. And then here, when x is 5, the y value is negative 751. And just based on polynomial knowledge, once it turns, it can never come back again. This is a 4th power, 4th degree. So it could have up to 4 zeros in the original function, but then it can have only 3 turning points. I found all 3 of the turning points. They are all the critical numbers, actually. So these are my only chances to even have any kind of max or mins going on. And this goes up forever on both sides, so it's never going to come back down again. So this is definitely the absolute minimum, and I had to do it by... The point is these two theorems don't always work, I guess is the point of this problem. So they both have special cases that need to be there. The extreme value theorem has to have a closed interval. The critical point theorem has to have only one critical number in the interval. If you don't get either one of those to work, then you just have to use other techniques, possibly. And or maybe you wouldn't be able to determine if there was a max or min, if it was too complicated of a problem. So there is no absolute maximum. I know that from college algebra. It goes up forever, just like problem 1 and 2 where you looked at the graph. And then there is an absolute minimum. Using a little bit of college algebra knowledge, I was able to figure that out. Negative 571, or no, 751, dyslexic moment there. 751, negative 751, and it occurred at x equals 5. Okay, so now here's a business problem. Total profit, P of X in thousands of dollars from the sale of X 100,000 automobile tires is approximated by this profit function. It is a polynomial, and X has to be greater than or equal to 5. Find the number of hundreds of thousands of tires, in other words, find X that must be sold to maximize your profit, and then find the maximum profit. So the number of tires sold to maximize profit, that's the location or the X value of the maximum, of the absolute maximum. And then the maximum profit itself, that's the Y value of it, the value that we normally look for. Okay, so number 9, I have a profit function of negative x cubed plus 12x squared plus 60x minus 200. And the interval is greater than or equal to 5. That's only half closed. That's 5 to infinity. That's not a closed interval. That's an infinite interval. So the extreme value theorem's out. I can't check endpoints and critical numbers. So my only hope here, unless I want to use college algebra knowledge, which we might be able to with this polynomial graph, is maybe there's only one critical number from 5 or higher. And if so, then I can use the critical point theorem. So let's see if that works. So let's find the derivative. The derivative of this would be negative 3x squared, then 24x, and then 60, and nothing. This is never undefined. It might be 0 twice, though. So set it equal to 0. I would factor out a negative 3 just so you can have a 1x squared, if you can do that. 24 divided by negative 3 is negative 8x. 60 divided by negative 3 is negative 20. This would factor potentially into 2 factors. You can even divide by negative 3 and that would be gone. So there's definitely one positive, one negative. Multiply to 20, subtract to negative 8. The bigger number has to be negative. So we have 1 and 20, 2 and 10, 4 and 5. 2 and 10 could do it. 2 times negative 10 is negative 20. 2 minus 10 is negative 8. So there's 2 critical numbers overall for the entire function because the actual domain of this function is infinite. Negative infinity to infinity is normally the domain of a polynomial. They put a limited domain on me because they are a tire company and they apparently make 500,000 tires at a minimum. So notice that negative 2 is not in this interval, but 10 is. That just saved us because now negative 2 doesn't matter. We only have one critical number in the given interval, even though the interval is infinite. So the critical point theorem applies. Now, I still don't know if it's a max or a min, but I have a chance for it to be. So if I check whether 10 is a local max or min, if it turns out to be a local max or min, then it'll also be the absolute max or min. So I want to plug it into the first derivative, or let me do this even. Let's do the second derivative real quick. It wouldn't take much to do the second derivative. Negative 6x plus 24. Here comes the second derivative test. The second derivative test is a little bit less work. You could still do the first derivative test if you want to, But if you plug in a critical number into the second derivative, and plugging 10 in here would give you negative 60 plus 24, that's definitely negative. Plugging 10 into the second derivative gives me a negative second derivative. That means when I reach 10 on the original graph, I'm going to be concave down, curved downward. And if you're curved downward at a critical point, a spot where the graph is flat, that has to be a local maximum by the second derivative test. See, to me, this was less work. I could have put 10 on a number line, and I could have plugged in, say, 9 and 11 into the first derivative. That's the first derivative test. And then I would have to hope that the first one was increasing and the second one was decreasing to prove this. And that's not that much work to do that, actually, especially if you have a calculator. Plug 9 in here, apparently you're going to get a positive answer. Then plug 11 in here, and apparently you'll get a negative answer. And then it'll switch from increasing to decreasing. That's a way to show that you have a local maximum. But to me, that's more work, especially with these bigger numbers here. I was quickly able to get the second derivative, and I can just plug my critical number into the second derivative. If that comes out positive or negative, then you instantly have a local max or min from one calculation instead of two. But it's always your choice. You can do first derivative tests or second derivative tests anytime you're checking for local max and mins. So by the second derivative test, I was able to prove that 10 is a local maximum by either the first or the second derivative tests. And in fact, if you did them both, you would never get different answers to that either. So either way you want to do it, first or second derivative test, there is a local maximum at 10. And because it's the only critical number in the interval, then by the critical point theorem, 10 is also the absolute maximum. So this company should try to reach 100,000 tires. That's when they're going to maximize their profits. And the maximum profits would be plugging 10 into the original problem. So if I do negative parenthesis 10 raised to the third power plus 12 parenthesis 10 squared plus 60 parenthesis 10 minus 200, 600 is the answer for the value of it. So there's an absolute maximum of 600, although maybe that's in some kind of units I'll have to adjust for, when I sell 100,000 tires. So X is the 100,000 tires. Profit is in thousands of dollars, so I actually need 600,000 apparently, since the units are in thousands of dollars. So they'll maximize their profits of $600,000 if they sell 100,000 tires. That's the absolute maximum. This is exactly what businesses can figure out and strive for, and that's how they try to shoot for their maximum profits. And clearly they only care about maximum profits. They wouldn't care about minimum profits. So that's where the critical point theorem can help. If there's only one critical number, that may be the one you're interested in. Okay, final problem, find the minimum value. See, now we only care about minimum. If we're doing cost, we want to minimize our costs. But if we're doing profit, we want to maximize our profits. Find the minimum value of average cost if you're given the cost function. And there's a part A from 1 to 10, part B is from 10 to 20. Notice that they're closed intervals though. So now we're going to go back to the extreme value theorem because I have closed intervals. This is kind of good how problem 9 and 10 are two business problems. One incorporated the critical point theorem, and this one's incorporating the extreme value theorem. So C of X, the cost function, is X cubed plus 29X. Whoops. Plus 432. Okay, so two things here, though. They said average cost. That was something we talked about earlier. Average cost is written C bar of X, and it's always found by taking the cost function. You know, in an average, how you add everything up and divide by how many there are. That's how I remember this is you take the cost function, you divide by X. It's kind of like dividing by how many there are when you're doing a normal average. So what it does is it makes each exponent decrease by 1. X to the third divided by x is x squared. 29x divided by x is just 29. And then 432 divided by x is literally that. So I have to get the average cost function first. Now I want to do the derivative of that because I want to find critical numbers in this interval. Well, I just need critical numbers in my closed intervals. So the derivative of x squared is 2x. The derivative of 29 is nothing. And if you rewrite this term as 432 x to the negative 1, then the derivative of it would be negative 1 times 432, negative 432. X to the negative 1 minus 1 would be negative 2. Or we could rewrite this 2x minus 432 over x squared. We had one like this earlier too. So part A wants me to go between negative 1 and 10. I mean positive 1 and 10, sorry. Positive 1 and 10. So I have a closed interval from 1 to 10. Are there any critical numbers here that I need to add to my list? So if x is 0, then the bottom of this will be 0. And that would make the derivative undefined. And it does make this undefined too. I was going to go up here, but we should be looking at this one. And that won't matter anyway, but 0 is not technically a critical number because it makes both the derivative and the original undefined. But 0 is not in my interval anyway. So that's not a critical number. And then finally, what would make this thing equal 0, if anything? And then I could add the negative fraction over to the other side again. And you can put this over 1 and cross multiply, or you can just multiply these two. So you would get 2x cubed equals 432. 432 divided by 2 is 216. The cube root of 216 is 6, actually. So 6 is the only number that makes the derivative 0, and there's nothing that makes it undefined. 6 is in this interval, so I would need to have an f of x column for 3 numbers only. All I would have to check is 1, 6, and 10. And there's definitely a max and a min, but we're only caring about minimum cost. We don't care about maximum cost. We don't want to waste money and spend more than we have to. So all we need to find is the minimum one. One of these 3 is guaranteed to be the minimum since I have a closed interval. So plug them back into the original function. 1 is easy because you're just going to get 1 plus 29 plus 432. 462 is what you get when you plug 1 in. If I plug 6 and 10 in, that might be harder. So 6 cubed plus 29 times 6 plus 432, that's 822. So that one's already out because I don't care about maximums right now. And then repeat it for 10. 10 cubed plus 29 times 10 plus 432. 1722. So the minimum of these 3 answers is 462. That's the absolute minimum. And it occurred when x was 1, which happened to be one of the 2 endpoints. The minimum value of the average cost, round to the nearest tenth. Okay, does it say that these are in anything but dollars? It doesn't appear to be. So that would be $462 is our minimum cost. 462. The endpoints. Oh, I plugged it in the wrong one. Okay, I know what I did wrong. I plugged them back into this, but once we found the average cost, we didn't need this function anymore. So scratch that idea. Let me start again. 1, 6, and 10. I'm supposed to be plugging them into this. I should maybe write it this way so I don't mess up. C prime of x is where you're plugging them into. So right here is what I need to plug them into. So 1 is still easy because 1 squared is 1. There's a 29 here, that's 30. And then this divided by 1 is 432. So that's still 462, oddly. But clearly that's not the answer because I already got that one wrong. So what would happen if I plug 6 or 10 into this function? 6 squared plus 29 plus 432 divided by 6. When I plug 6 in, I get 137. That's already less than it was for 1. So yeah, 1 is out. So the minimum cost might be $137 if I make 6 of my product. Or what happens if I plug 10 in? Can I get it even lower? 10 squared plus 29 plus 432 divided by 10. It's a little higher, actually, 172.2. So absolute minimum is $137. $137 is the minimum. I see this is what a business needs to know. They need to plan for this. It's going to cost you a minimum of $137. So if you don't have that money, you can't even start your business. Absolute minimum $137 if you make 6 of your product. And this would actually turn out to be the absolute maximum, but it's not anything we care about right now. So $137 is the absolute minimum value. Since I plugged it in the wrong function is why that was wrong. Then repeat this for what if your interval was 10 through 20? If the interval happened to be 10 through 20, closed interval still, well then, what was our critical number? The only critical number was 6. 6 isn't even in that interval anymore. So then our whole list would just be the endpoints. We had one of those earlier too, where there were no critical numbers in the interval that we cared about. So all I have to check is 10 and 20. And we already did 10, it's right here, 172.2. So one of these is the max and one of these is the min, but we only care about the minimum right now. So plug 20 into this average cost function. 20 squared plus 29 plus 432 divided by 20. Is this higher or lower than 172.2? It's higher, 450.6. 450.6. So now this is the absolute minimum in this closed interval, and this is the absolute maximum in this closed interval, though we don't care about that. So $172.20 is your absolute minimum if you're going to make between 10 and 20 of your product no matter what. So usually a business will know how much product they're either willing or able to make in a given time period. So they can know this ahead of time, and then they can plan for their minimum costs. And it's probably going to cost more than the minimum, but this is the minimum they got to have. So they got to have $172.20 or they're never going to be able to do their business that day. Okay, so we finished 6.1, 100%, 10 out of 10 points. Again, it mostly comes down to these two theorems. But we saw one problem where neither one of them works. So the extreme value theorem is nice because then you're guaranteed to get answers. In fact, you're guaranteed to get both answers. The critical point theorem is more like a saving grace, where it seems like maybe you can't get an answer, and it might save you if there happens to just be one critical number in an interval, but that's a very special case. And then otherwise, then you can just resort to other things like I did with the problem number 8, where you might just have to resort to other knowledge in order to find these points. So that's it for section 6.1.